Hi folks, 4.4 is circular motion, which is pretty interesting stuff. Linear and angular speed. If you recall the famous definition of distance equals rate times time. So average speed, if you solve for r here, is distance traveled over the time elapsed. So we say that the average, and we're not going to use that word average, but we're just assuming it linear speed of an object, and they're saying it's v is equal to, and in this case we're talking about along the edge of a circle. So if we're talking about the distance traveled along the edge of a circle, that is arc length. So in the numerator, we're dealing with arc length, and in the denominator, it's versus some unit of time. So you have to pay attention to what your units are. The other thing that is interesting is angular speed. Angular speed, and they use the Greek letter omega, is distance, not distance in this case. It's the change in the angle, theta, and theta is measured in radians. So the change in radians over time. So we're not going to use the word velocity in this because we're not indicating like a direction. And if you ever get into physics, you'll have velocity, and it'll depend on the sign of like which direction you're going. It could be negative or positive. So a modification of the two formulas that we were just looking at, and I wrote them right here, 4.8 and 4.9, is that the speed, linear speed, is equal to angular speed times the radius, and that is from up here because you know that velocity, I use velocity, linear speed is s over t. S is arc length, so if you recall that s, arc length, is equal to r times theta. So if you substitute that in and you put r over on the side, theta over t is omega. So we have omega, which is equal to theta over t. So if you substitute that, then you have this nice new formula. So the examples in the book are really great, and I recommend you just read through this section. It's pretty, I bet you could actually do it on your own without even watching this lesson, but this is just a little extra stuff. So to actually find angular speed and linear speed, which is what you have to do in some of the exercises, in this case we're given the radius, and that's 8 meters. We're given the time, 2 seconds, and theta. So what I would first do is use 4.9. So 4.9, we can say that omega is equal to theta, which is 3 radians, over the time, which is 2 seconds. So if you calculate that out, 3 over 2 is 1.5 radians per second. Okay, so once you find this is angular speed, anytime it's dealing with radians, it's angular. Okay, and then to find linear speed, we know then that linear speed is equal to omega times the radius. So we have 1.5 radians per second times the radius, which is equal to 8 meters. Okay, now radians, I don't know if you remember me saying this, but radians are basically unitless. That's another reason why they're such a nice unit of measure to use for angles. So if you multiply this out, you can find that, and I'm just not going to use my brain today, forgive me, 8 times 1.5. I can do that. That's actually just 12, isn't it? We'll just double check. Yeah, that's 12. So if we multiply that out, we get 12. And what I was saying is basically, since they're unitless, they can kind of go away. Isn't that convenient? So 12 meters per second. And just make sure that your answer makes sense. If you're dealing with linear speed, then you're talking about some unit of measure that measures length, right? So it's like linear line, meters per second, versus angular speed. You're measuring an angle over time, so it's radians per second. So once again, we're trying to find linear and angular speed, and I'm given the radius, the time, and arc length. So first I'm going to find linear speed because I have S and T. So it's 3 meters. And I think it's handy to have your units with you so you don't forget in the end. So it's 3 over 1.6. So let's just see, 3 divided by 1.6, and that is 1.875. So that's 1.875 meters per second. All right, so now we know velocity, or I keep saying it, linear speed, and now we need to find angular speed. So I'm going to use this formula, 410, because I also know, do you see that I have the radius? So if I solve this and I say, okay, omega is equal to linear speed over the radius, then I can find this easily. So omega is equal to velocity, excuse me, look at me, I'm so used to that V. That's meters per second. So that's linear speed over the radius, which is 1 meter. And in this case, we have 1.875 meters cancel out. And you can just tack on the radians because you're dealing with angular speed per second. Just like you can taketh away, you can putteth in. So in the textbook says, in physical applications, you can see that angular speed is given in revolutions per minute. And in number 11, you're asked to find basically the speed of the dust on the outer edge of a record in inches per second. So you're going to have to convert from revolutions per minute to radians per second, or whatever your unit is. And since they want radians per second or inches per second, you should deal with seconds. So here's the example, and this is in your book too. So let's just let's just come up with let's just suppose that we have let's do a nice number, 90 revolutions per minute. They're just doing it for n. So what you do is you say, okay, well, 90 revolutions per minute, and I should have written it as 90, you know how you used to do, you've probably done this in the past, use your revolutions, write it as a fraction per minute, and then you can say, well, I want to get rid of the revolutions, right? Do you agree that one revolution all the way around a circle, remember, in terms of radians, that's equivalent to 2 pi radians. Okay, so then I can cancel out those. And then what is, that's not equals, this is times. And then I need to get rid of my my minutes right down here. So I can say that 1 minute, and I'm trying to get seconds, right, per second. So is equivalent to 60 seconds. So I'm going to cancel out these. All right. So now I have 90 times 2 pi radians. And then I'm down to radians per second, which is what I wanted. And that, remember, is angular speed. So now I have the angular speed versus RPMs, and that's 180 pi. So you could just say that's 180 pi radians per second. And that'll help you with number 11. 4.17 is similar to 8 and 9 that I assigned, and basically, if you think about it, and it took me, I don't know, some time. If you picture a particle on the outer edge of each gear, so here's a little particle moving along the edge of a gear, and here's another particle, and you start spinning these gears, the distance traveled, like over so much time, is actually going to be the same distance, even though this one makes more revolutions. So that's the hard part to imagine, that this smaller gear is going to spin and go around more times than the larger gear. But the distance, the outer distance, S, the arc length, is exactly the same after a certain time. So then they developed this idea that arc length is the same. And since arc length would be equal to V1t and V2t for the second arc length, we can set them equal to each other. And then we get this nice formula right here with angular speed and the radius. And so then in this case, they give you the radius for the larger gear, and they give you the angular speed for the smaller gear, and they also give you the radius for the smaller gear, so you can find that it's 20 RPM. So we didn't have to convert this back to radians per minute or anything like that. So those problems are very similar to this, so you should be okay. And I think that's basically it. If you have any questions, you can always send me an email, talk with the AAC, a tutor there, or come visit me during office hours. Have a great day.